If you go out on the show floor here, you'll see some undergraduates setting up clusters on the left-hand side of the exhibit hall. They're frantically building their clusters right now, putting components in racks and figuring out that what things broke and shipping and so forth. And we'll talk a little bit about some of these characteristics, the history of the competition, past competitions, why these are valuable and why they're becoming popular, and some interesting observations that we've made from the University of Colorado. The creator of these competitions, or the concept, came from a guy named Brent Gorda, who's now the CEO of Wham Cloud. We had a meeting at the end of SCO6 in Tampa, and he sort of threw this idea out there and said, do you think this would be valuable to have an undergraduate competition? And there was a lot of interest around it. And the goals of this were to sort of to bring up the next generation of HPC admin and talent, and to introduce more scientific computing and HPC computing into the undergraduate curriculums. At most universities that I've been to in the States, HPC is solidly in the realm of graduate work. Most of the work is done around specific scientific disciplines, specific applications, improving performance, getting models that will scale, things like that. But now, it's kind of the industry has evolved to a point where you can push a lot of this technology down, right? Linux is very popular. These commodity off-the-shelf hardware is becoming more and more popular in your data center. So a lot of these things can be pushed down. The other thing too is that HPC runs in a data center. Data centers are typically behind locked doors. The undergraduates usually don't get much access to the hardware, much hands-on access, right? The stuff's expensive. You're not about to let a group of undergraduates go run amok in your data center and start pulling components apart and things like that. So this is a way to get them real-world hands-on experience. So after the meeting in Tampa in 2006, we held the first competition in Reno, Nevada in 2007. And what you see here are the competitions since the winners and the highest LINPAC. So they typically give 2 awards. You run the HPCC benchmarks and LINPAC, and then you run a suite of applications that are chosen by the judges. And these are real-world applications that come out of live research from a variety of disciplines. So this shows sort of who the past winners are and the past highest LINPAC winners are. We get teams from all over, so it's truly an international competition. We started out with 6 teams. We grew to 8. We started out getting, the teams have to submit a proposal. You submit the proposal in the spring, and the proposals are prejudged, and then you get invited in the fall. So, what's the real world from this, right? What are these students going to be asked to do? So most of your HPC installations are in a data center, right? And what do you need in a data center in order to run these things? You need space, you need power, and you need cooling. So the students are given a 10 by 10 booth. So that's their space, right? Everything be contained in that 10 by 10 booth. They're given a limited power budget that they're penalized if they go over that. So they're given 2 120 volt, in the States, 120 volt circuits that are limited at 13 amps, right? So that's the main limitation. You can only get so much computational power in that power envelope, right? And then cooling traditionally hasn't been a problem, right? We've used ambient cooling. With that amount of power, ambient cooling seems to be fine. The past 2 years, there's been a little bit more innovation in that. University of Texas last year brought a liquid-cooled system, which was cooled by mineral oil, which was very efficient and allowed them to get much more computational potential out of their system. But because you're under the power limitation governs your computational system. So my laptop doesn't go on that power limitation, but all of my compute nodes do. If the cooling system is is necessary to make your computational system run, it's on the power budget. which means the pump that circulated their mineral oil had to go into their power budget. So we're giving these undergraduate students, hundreds of thousands, sometimes hundreds of thousands of dollars worth of hardware, and we're saying, go out and build this cluster that'll run these applications under this power limitation. What's two things? What are the takeaways? What's the value to this kind of competition, right? Well, I went out and I grabbed a couple things from Top 500. The two charts on the right show you what the majority of the OS and vendors are for the types of hardware on the Top 500. If you map those against what gets used in the competition, they map up very nicely. Well, what does this mean? This means that these students are getting access to an experience and hardware and software that they can directly take into being employable after graduation. Right, so you see the list of vendors and the type of software that's most popular in the competition that the students bring. They're allowed to go out and get any kind of hardware that's commercially available. They're allowed to use any kind of software that they can get their hands on. They're allowed to do anything that everyone has access to, all the teams have access to. Right? So for instance, one year we had a team partner with Intel, and it was when Intel was going to release Nehalem, and they ended up pushing their release date, right? Which meant that they weren't going to announce that processor at supercomputing, so we had to come up with other plans. So sometimes you get access to, the students got access to pre-release hardware that computing centers across North America were vying for, right? And this school actually got 20 Nehalems delivered before anybody else. That was actually my school, but and then Intel came to us and they said, "Oh yeah, by the way, the day before the competition started, by the way, we're not going to release those, so you can't release any numbers." I mean, we had LinPack numbers, we had application numbers, so that was fun. So you see, these are all common things that you run back in your data center with your applications, right? They're very popular. So originally we had about 10 teams submit proposals for 07. This is a randomly selected pool of schools that have submitted proposals for the past couple of years. We only have 8 slots to fill. There's 8 teams that we invite. So the proposals now have come from enough schools that it's not enough that you show me you have a partner to vendor partner and that you can get a cluster together. Now in the proposals, you've got a performance statistics. You've got to show me that you've actually compiled and run the applications. And you've got to show me that you've put some seriousness behind this. All right? So the students are doing a lot of work. And in many instances, this is in addition to, or this is an extracurricular activity to their normal undergraduate workload. So for us, how do we measure success of this kind of a challenge? What this slide shows is that this competition has been going on for 5 years. In 5 years, we've had about 17 students. Each team, each year, is made up of 6 students. We've had about 17 students go through this cluster challenge type of experience. So the first thing that means is that students are interested enough that they stay in it year after year after year, right? I've had students on teams for 3 years. All of the numbers here represent immediate employment upon graduation or before graduation. So of our 17 students, we have had 9 students immediately employed in the HPC field at these organizations. So 2 at Oak Ridge, 1 with the U.S. Navy, Lockheed Martin, Google, Los Alamos, places like that. So is this bringing new talent into the HPC field? I think this demonstrates that it does. Does this demonstrate that the HPC and scientific computing can be taught at the undergraduate level? I think it does. This also demonstrates that there's enough interest to inject more of this into the undergraduate curriculum. So, the applications that the students are expected to run at the competition come from everywhere, right? Molecular dynamics, biology, fluid dynamics, astronomy, physics, weather, from all over. Our team has tried to recruit people from all over, not just computer science and electrical engineering. Economics, biology, astronomy. We've had students from all those different disciplines on the team. They don't have a traditional computing background. Like I said, we've had students year over year, which is nice because we can build their experience from year to year. Maybe one year you just take responsibility for optimizing an application. The next year you can take on a little bit more. Out of this, we've had 3 student undergraduate research papers written, one of which won a Best Undergraduate Paper at the LCI conference. We've had 5 faculty papers or presentations done based on this experience at various conferences and gatherings. So we've been able to submit a proposal for 5 years and have been at our school and have been invited to compete for 5 years. So we've been able to show that we put forth a serious effort. Our school has purchased a fairly large cluster, the 13,000 node cluster. They've also injected new curriculum specifically for HPC. So most undergraduate curriculums, you might get an elective exposure to scientific computing, right? You might get an intro to HPC where you learn how to compile LNPAC and you learn some basics of HPC. Now we have a scientific computing course because of this. We have topics in high performance computing specifically based around this competition, so kids can now get course credit for it. We also have internships at our research computing facility as well as NOAA and NIST, specifically that have grown out of this type of event. So the interesting things that have come out of this competition, bringing the fastest hardware does not give you an advantage, right? For the first 4 competitions, unaugmented clusters with the fastest clock did not win the competition, right? So it's more about knowing the application than just bringing the fastest hardware or just bringing the most hardware. GPU augmentation, now more than 50 in the competition have some kind of GPU augmentation. 5 years ago, there was 0. In 07 and 08, there were no GPUs. 09, we saw the first GPU augmented cluster. The important thing that we see there is skill sets are now starting to transition, right? GPU programming is still sort of in its early stages. The tools aren't there yet, and that's a hard area for even a graduate student to begin to make significant progress on some of the applications. For instance, at NCAR, on a project using WRF, they put 3 PhD candidates to work optimizing WRF for GPUs. They spent over a year working in just one of the physics modules. Come to find out, 3 PhDs, a year later, they improved it by almost 30, they improved the physics module by 30%. Well, the model only spends less than 20% of its time in that module. So the payoff wasn't quite there yet. You know, those things are coming. But now you're starting to see GPU-enabled clusters. What this means for an undergrad is I hand them 4 or 5 applications that I've chosen out of thin air, okay? You get to decide, is it an application that I can port to GPUs? Does it get a performance enhancement? Or is it better left to just run on commodity CPUs? That is well into the realm of graduate work. And undergraduates are now getting some exposure to that. We designed the competition to be a challenge, right? To make it hard, right? There's plenty of meat there in this topic to show improvement in an application. You know, when you handed me this and I compiled it with GNU, it ran in 3 clock hours. 2 weeks later, I've played with it, I've tweaked it, I've learned what these compiler flags do, I've learned about how to structure this on the cluster. It now runs in an hour. So there's an empirical aspect to this that's different than anywhere else in the community. The competition in the States runs 48 hours straight. So the students are camped out there for 48 hours. One of the things we learned is if you put caffeine in it, a student will eat it or drink it, right? I think in the past couple of competitions, we've exhausted all the Mountain Dew within a pretty good radius. They sleep with the hardware. The fun thing about this was the very first competition in Reno, right? Supercomputing draws in the States draws somewhere around 10,000 people. The second day of the competition, you're right in the middle of it, and what happens? Power goes out for the entire convention center. So you know, I don't know. There was a Register News article on it, but what do a bunch of computer scientists do without electricity, right? For 30 minutes, you stand around and yak. Students totally lost it, right? The thing that they had been working on for 6 months, all of a sudden didn't work. So they get to stand around and twiddle their thumbs for 30 minutes. Then the power comes back on, right? Jobs stopped in the middle. You don't know, oh man, did I set this model up to checkpoint? Right? So they get to, here's the real world aspect of it. I've worked in data centers for going on 20 years now, and this has happened to me, right? It's trial by fire. That's often when you learn the most, especially about the things you should have done. So all of these experiences combine together to make an educational opportunity that's totally new, that we've demonstrated, I think, that makes real world sense, and that is bringing some new blood into the computer science, the HPC industry. When I asked my students, I said, when you started your degree program in computer engineering or in biology or economics, did you ever consider going into an HPC area? And they say, no, that wasn't really on my career track. But now those very same students are working at the places we showed, at Oak Ridge, in the Navy, at Lockheed Martin, things like that. So I'm happy to answer any questions. Presentations maybe a little more thick. Yep.
So how does this competition primarily, what's the primary difference between the one at supercomputing? Is it just the hours that the kids are working, or what would you say?
Yeah, I think Gilad made a good comment earlier. This one is much more humane. Right, the evenings are open. You know, and the students have been spending hour upon hour prepping for this, right? My students have slept very little up until about a week ago when the cluster had to actually ship here, right? And there was this big sigh of, we're done, right? Here, there are some interesting differences between this competition and the one in the States. The hours are different here. Also, we don't know what a couple of the applications are. Typically, at the competition in the States, in February or March, we say, okay, this year's competition is going to be WRF, POP, NWChem, and games. Those are your 4 applications plus LINPACK, right? And keep in the back of your head, these students know nothing about molecular dynamics, right? I know nothing about molecular dynamics. So they're going to dive into a totally new scientific discipline that they've never seen before, and that they don't even, in many cases, don't even have the prep for. But they can dig into these applications and they can say, okay, well, the cluster in some ways is the petri dish. Compile it, throw it on there and run it, and see what blows up. All right? So here, two of the applications are going to be unknown. They're going to have to build them, compile them, optimize them on the fly. So the hours are different. Applications are a little bit different. We don't have as much experience with some of the European models. So, experience with POP, I don't know anything about Nemo. Plus, many of my students have never been out of the United States. So this is a totally fantastic opportunity for them. Yes? 16 to 25. 16 to 25? Yep. Do you know how many were here for the IC competition? There are, 4 teams here? 5 teams. How many? Around 10. And
that's the first time we're doing it here.
Yeah, some interesting things around bringing a team to a competition like this. Many people go, you sit back and you say, okay, you get to take a cluster to go compete, and these are the metrics or the parameters of your competition. And people go, oh, well, I'd go get this hardware, and I'd go get these processors, and I'd do this and this and this. From a school perspective, I have to partner with a vendor, right? And so in some aspects, there's a saying, beggars can't be choosers, right? So the university doesn't give me a budget and say, here, go buy all this hardware. I partner with a vendor, and I see what the vendor can give me, and we go through building a system that way. The nice thing is that the students get some partnerships with actual industry people, mentorships. This opens up doors for internships, things like that, so that they get some real-world exposure, right? It'd be really cool, if I'm going to go to a car race, bring a car to a car race, I'd love to bring the Ferrari. My budget will only get me, the Toyota or the Honda. So in many ways, bringing a team does the same thing. We partner with a vendor. The vendor says, this is the hardware I can give you. And you also get the real-world lesson of working with some partners who say, you know what, I'm not going to release this processor, so you can't use it. That year, we actually went out and sort of raked over the show floor, and we built a cluster. Cool sidebar, in Austin, competition in the States usually starts 8 o'clock Monday morning. You run LinPack, right? So about 2 in the afternoon, after we had run LinPack, Intel calls me and said, I'm going to release this. You guys can't release any numbers. You can't use that cluster. LinPack has to be in by 5 o'clock. So we pulled the students aside and we said, it is what it is. You can either decide to fold or you can find some creative solution to the problem. So they went out and they canvassed the show floor, right? Between, third week in November, second week in November, there's probably not anywhere in the world there's a higher concentration of HPC hardware except at SC. So they got creative. They went out and they collected enough stuff to build a cluster and run LinPack and submit a number that wasn't in 3 hours. So that wins right there, right? At the SC competition, and I think it's the same here, I can't help my students during the competition. They're on their own, right? I have 20-something years of doing this. They have maybe 2 or 3 months, right? So when the power comes back on at Reno after power failure, they got to troubleshoot why things didn't come back up. We actually lost an InfiniBand adapter, and it took them 3 hours to troubleshoot that. But they came up with it, and they got it replaced. So that's, those are the kind of experiences that come out of this kind of initiative. Any more questions? Yeah.
I enjoy also participating on this contest
Yeah, so we've had, out of, and I think we talked a little bit about this, we've had 3 student papers that are purely student papers come out of this, which were peer-reviewed and presented at either the LCI conference in the States or at supercomputing, not last year, but the year before. There hasn't been a requirement in the competition for presentation other than the last day of the competition, or the competition organizers usually assemble a group of judges. The judges are folks like Jack Dongara and Jeff Kuhn that are notable in the HPC world and who can judge the applications. And they come along and they interview the students, all right, at the very end of the competition, right before the winners are announced. They interview them. In the past, the students have had to actually do the visualizations from the models, right? So that's another component, and actually discuss a little bit, some basic intro material about what the visualizations show. And on a team-by-team basis, I don't know if all the teams have written papers or not. I think Stony Brook might have. I know Purdue has, and we have. But that's, we do emphasize that, the presentation and authorship of papers. We think that gives them a little bit better idea of, a more well-rounded experience.